All right. Hello, everyone. Welcome to this talk on debugging your hardest bugs with time travel. So I'm Greg. I'm co-founder and chief exec at undo.io. We make a time travel product, but this talk is going to be more general about how the technologies work in general, the different tools that are available. I may mention our own, but not exclusively. So here's the thing, right? I reckon most programmers spend most of their time debugging. It's sometimes said that programming is made of two parts. There's bugging and debugging, right? It's typing the code in and there's making it work. And, well, unless you're a significantly better programmer than me, most of the time is spent trying to get it to work. And actually, most of that trying to get it to work is to understand what actually happened, right? I wrote the program, what really happened. And so, yeah, I think debugging completely dominates software development. And I feel that as an industry, as a craft, we just don't spend nearly the appropriate amount of time talking about it and working on it and getting ourselves to be better. Think Kernighan. You probably know this quote from Brian Kernighan, the great inventor of C and Unix and many other things. And he said it better than I can. I think he says everyone knows that debugging is twice as hard as writing a program in the first place. And so if you're as clever as you can be when you write it, how will you ever debug it? And I think what Kernighan is getting at here is like, keep it simple, right? You're perhaps not quite as smart as you think you are. Give yourself a bit of margin for error. But I think there's also a really interesting corollary to this, which is like debuggability becomes the limiting factor in how good our code can be. Like whatever your metric for good is, how fast it runs, how small it is, how quickly you can write it, whatever your metric for good is. If you're twice as good at debugging, you can make your code twice as good. Or put it another way, you cannot be a great programmer without being great at debugging. And part of that is using the tools that are available to you and knowing when to use which tools and what tools are available. You've come to this talk, so like I'm preaching to the converted a little bit. But let's think about it, right? How do we debug? So debugging dominates software development. I'm talking about, how many lines of code do I back myself to type in and have it work first time? Like really 10, maybe? How many lines of code can I change and have it work first time? I reckon that averages to less than 1. So we spend a lot of time debugging, and there's different ways and tools for debugging. So maybe we use dynamic checkers, Valgrind, address sanitizer. I have other talks on that. I'm not going to talk about them today. Just a good old debugger, right? Whether they're IntelliJ if we're doing Java or GUI or VS Code or like CLion, lots of good debuggers out there. Dynamic logging. So there's things like Lightrun that let you sort of add these implementation points to your program. But you know what? Probably it's just Printf or some equivalent of, right? That's what I reckon 90%, probably more, 95% of debugging is just add another Printf and go again. Why do we do that? Well, I think there's a couple of reasons why people do that. And I think maybe my sort of slightly hot take is that it's kind of just laziness, right? It's our happy place as developers. It's the developer's version of just reading email. You can kind of tell yourself that you're busy, and you're just adding a Printf and recompiling and rerunning. And it's like, oh, okay, now I need another Printf. But no, this will be the last one. All right, I'll get it on this go. And of course, it's, often it needs many, many. So they probably know this old XKCD cartoon, that they're saying, get back to work when my code's compiling. Obviously, this is kind of pre-pandemic. But anyway, why is it compiling? Well, it's compiling probably because they added a Printf. So I think there's just the laziness to it. It's kind of our happy place. But I think there's something else as well, right? It's not all bad. There is a point where Printf actually is useful. And that's it gives you this story of what happened, right? What the code did. And regular debuggers don't really do that for you. Okay, so when we're debugging, we want how did that happen, right? We're thinking in the past tense, what actually happened? I had, I don't mean like, how did that happen? Or how did that happen? But I mean like, I had a set of expectations for what my program was going to do. And then when I ran the program, something else happened. Reality diverged from my expectations. And the process of debugging, 90% of it is actually just figuring out where was that divergence? What actually happened versus my expectations? Actually, usually does something like that. But that, most of the time, fixing the bug is quite a small part of the work. Perhaps it's even like sometimes it's removing a line or adding a single character. Or it's usually fairly straightforward to fix the bug when you know what's happened. It's finding out what happened. what your program really did as opposed to what you expected, which is usually the big challenge. Okay. So what do? So we keep running and or ignore that URL, that shouldn't be there. Anyway, we keep running the program with printfs, and we kind of run again and again. And each time we get another clue, we get another piece of the jigsaw puzzle of what actually happened, and we fill in the reality. And then eventually we kind of get this magic piece of the jigsaw and everything kind of becomes clear. Maybe we can think of it as like some sort of Sherlock Holmes. We're just getting clues, right? And we're one by one building up the clues until we have we've eliminated the impossible, and then what we have is the answer. Actually, sometimes it feels a little bit less like Sherlock Holmes and more like that. But anyway, you're probably familiar with this. And there's a couple of things I think that a couple of dimensions that make bugs hard to fix. I've said fix on the slide here. Really, I think what I mean is make bugs hard to find, but most of fixing is finding, so it works. So first thing that makes bugs hard to find, to tell us how hard a bug is how long is there between the bug itself, that piece of code going wrong, and the failure, right? Maybe the assertion failure or the seg fault, or God forbid, the program kind of completes but gives bad results, right? That's always the worst one. So the longer that gap is, the harder it is to fix. And it might be, a second or two, and that's a long time in computer land. It might be hours if you're really unlucky. And this is why, by the way, this is why assertions are so powerful, right? What assertions do is they narrow that window between the thing going wrong and you noticing. But, it's usually not instant. Sometimes it is, right? Sometimes you get, I don't know, the pointer could legitimately be null. I didn't check for null when I dereferenced it. I get a call file. It's there. The line of code is like the time is that length of time is 0. The bug is right where the bad line of code, is where I see the symptom of the bug. But yeah, often not. The other dimension for what makes bugs hard to fix is how deterministic are they, right? How repeatable. Every time I run it, maybe it only fails one run in 1,000, or maybe every time I run it fails, but in a different way. And so as I'm getting these pieces of the jigsaw puzzle in my different runs to understand what happened, it's like every piece is for a different puzzle, okay? And that gets really, really hard to fix. And of course, life gets particularly fun when we get right in the top right-hand corner of here, right? We've got both long time between the bug and noticing the failure, and this kind of non-deterministic behavior of the bug. And really, really fun when we're right here in the Heisenbugs, right? This is where we've all been there. You add a print statement and the bug goes away. Breaks. So it's like, well, maybe I'll just ship the print statement, right? But usually you don't want to do that. So that's kind of the context here. This is where I think time travel gets really significant. So with time travel, actually I've chosen here the picture of, this is the H.G. Wells time machine. And I chose this because rather than one of the more modern kind of sci-fi time travel things, because, partly I just think it's cooler, right? But also because in this story, the time traveler is an observer. He's not trying to affect history. He's just trying to observe. And that's what we're talking about here. We're not talking about going back in time and like fixing the bug and then just, rerunning the program in some, but that's kind of, that would be interesting, but that's a really different thing. What we're talking about here is just going back in time, winding back, kind of like CCTV is perhaps another metaphor, right? Winding back time and seeing what happened. So enough just talking about what the problem is and why we want time travel. I'm going to show you really, really quick, simple demo of how it works. And so let me get to here. So I'm showing you this demo. This, by the way, is a very small program. It's like not even 100 lines of code. And I'm showing you it in VS Code. The modern time travel implementations really do scale, right? There's stuff you can run at programs basically as big as you can imagine. I mean, we have customers who run programs that are in the terabytes of working set, terabytes of RAM, and run for days, okay, in the extreme case. And sometimes it's much smaller, right? So both this is scales from tiny programs right up to really big programs. And most of the modern time travel implementations do that. So in the last few years, time travel debugging has come from a kind of a toy. If you've ever experimented with the built-in GDB process record, you'll know it really is kind of a toy. It only works on even this program actually is too big to run with process record. But the modern time travel implementations, yeah, they really do scale, and that's kind of the key thing. And we'll talk about in the second half of this talk, I'm going to talk about like how that happens. But for now, let's just see what it is. So what's happened here? So I've got my program loaded into the debugger. Yeah, so this is VS Code. You could be using CLI. You might actually, most people just run like GDB at the command line, perhaps in TUI mode, but I find the visual kind of thing just makes slightly better for demos because we can see more stuff at the same time. So here we are. So it's failed with this assertion failure, right? That's basically where we got to. And this assertion has detonated because this value, square root cache, is supposed to be the same as this value, square root 15, and it's not, so the assertion has failed. By the way, this program ran some time ago. In this case, actually, it ran a couple of hours ago, but maybe it ran last week. It doesn't matter. We've got a recording of that program execution. And so it's like kind of like looking at a core file. If I had a core file of the crash, kind of could do all this so far, right? I can see, yeah, square root cache is 0. It should be 15. I can kind of look at this code. I've called this cache calculate and just passed in number. Number I can see is 255. And yes, return 0. And it looks like it should have returned the square root. And it didn't. I could do all that with a core file. But the thing with a core file is it's just the state at the end of the program execution, right? It's the state at one moment in time. And here, the bug is a little bit before I've noticed it, right? A little bit before that assertion is detonated. And with the core file, I'd be kind of stuck here, right? I need to know a cache calculate returns the wrong thing. It was supposed to return 15, it returned 0. Why? How did that happen? Okay. And with the core file, I don't know, right? But with time travel, check this out, right? We can just wind the clock back. So here, look, I've got these are the normal kind of stepping buttons that you expect to see in a debugger, except we've got backwards ones as well. So I'm going to hit this one, and we're going to go back one line of code, right? Watch this. Back. And not only have I gone back in time, look, the data here is updating as I do so. So it's not just what lines of code ran, it's like what was the data. So as we said, we want to know why did cache calculate return the wrong thing? So I'm going to do this reverse step into, okay, so I've got the step into button here, which is a forward step into, which you're probably familiar with. This is the reverse step into. So it's going to go to the return point from that cache calculate function. So click here. So here's the return statement, right? And I'm returning, well, 0 as we expected. Got some threads going on. What's going on here? Actually, let's have a look at the threads. This is thread number 11 of like a bunch of threads. Got like, well, actually I've got 11 threads, and this is the 11th thread, as it turns out. Yeah, let's go back. Well, maybe there's some threading issues. But we can see we're returning from this global cache here. We've got some kind of cache. I is 90, and I've got it. I've got a watch for it here. So cache I tells me the square root of 255 is 0. Now, obviously, that's wrong, right? So my cache contains bad data. There's this classic, bad day at the office problem here, where the cache, someone's corrupted my data, okay, and I have no idea. Who did that or how it happened. Was it a threading error? Is it a logic error? Is it a pointer error? All I know is at some point, bad data has ended up in my data structure. Well, maybe it was a threading error. I've got some threads here. Let's get back in time to before this mutex is unlocked. And like maybe that will expose something. So here we go. Back. So that's before the mutex unlocks. So now I'm in the kind of critical section. It's still saying the square root of 255 is 0. So probably not that. You know what I want to do? I just want to see when did that happen, right? Something's written garbage into my data structure, and I want to know, like, basically who to blame, yeah? So let's just do that. If I select that, and now I'm going to hit this button here, right? And this is the last changed facility. What this is going to do, when I hit enter, we're going to go back in time to the last time that got updated, the last line of code. It's like a reverse watch point, if you're familiar with watch point or data breakpoints. So here I go, ready, enter, boom. Right, now I've gone back in time actually right after this was updated. Let's just go back one more line because it's going to be a little bit easier to see what's going on here. So, okay, so here we are, updating the cache. I is 90, that makes sense. I'm updating the 90 then from the cache. And look, here it is, contains good data. These are integers. So the square root of 40 with integer maths is 6. And let's just see that I'm really seeing what I think I'm seeing. I'm going to step forwards and watch. It's going to be like, this is a bit like action replay if you're watching sports on the TV, but watch the data here. I'm going to step forward, watch the data when I do so. So step, that's it. That's the badness right there. I've caught it in the act. That's the corruption happening. So what's going on? Well, we're writing into the cache, writing number adjacent, -1, and square root adjacent, which is garbage. So I tried to take the square root of -1, and I've got garbage, and I put that in the struct, and the struct contains unsigned chars, and that's kind of getting close now. But I often have this chain of like, why did that happen? Questions when I'm debugging something, the root causing something, right? So why is number adjacent -1? Well, Now, at this point, actually, I'm pretty close. I could probably do it with code inspection, but this is a demo, so I'm just going to show you a bit more. We've actually got a command line here. So you can, if you prefer the GDB command line style stuff, you can do that as well. So number adjacent is -1. Why is number adjacent -1? Well, let's just do another last command on that. Sometimes say this is the last command you'll ever need. So last number adjacent. Why is number adjacent contain -1? Okay, so we've gone back in time again. I've got this timeline, by the way. Here I am. Look, I'm almost at the end, but actually not. I'm just almost at the end of that program execution. But we've gone back a little bit. Number adjacent is, well, it's not initialized yet. It's being initialized to 0 minus 1. So here's the bug. I've called the function with a number of 0. It returned the right thing. It returned 0 as a square root of 0, but it was trying to be clever, and it's trying to keep a cache of previously calculated numbers, and it's assuming some kind of locality of reference. And so it's stored to square root of 0, 1, and oops, -1. And then I didn't notice many iterations later, my program just stumbled over that bad cache entry, right? So little example, actually hard enough to debug, right? I've challenged people to debug this normally just by looking at the code or running it a few times. Not that easy, trivial to debug in when you've got time travel. You can imagine if this was millions of lines of code, you can really, I hope, start to see why this is powerful, right? Obviously, I'm just showing you a small program because it's much easier to talk about, especially in this small slot. So isn't that kind of magic, right? Doesn't it mean the hardest bugs right at the top right-hand corner just become trivial? And even the easy bugs, right? I would say, yeah, sometimes, we literally have cases where people say, it saved them months and months of time, or made something impossible, even tractable to debug. And that's great. I mean, very powerful. But sometimes even better than that is like repeatedly turning an afternoon debug session into a few minutes, like the compounding power of that, or just understanding the code, right? Most of us work on code bases where, they're big, right? There are millions of lines of code, and we didn't write it all, and maybe we wrote hardly any of it. And, somebody very clever before has written something that's just totally opaque and not clear what's happening. And, how do the different bits and modules, how do they all interact and who calls what? So being able to just explore the code flow, if you like, just to see what happened is not necessarily even debugging, seeing how it actually works is also very useful. So that's time travel. I hope that you're totally amazed and wowed by that. You think, well, I'm going to go away and do it. We're going to talk about how would you do that? It depends what platform you're on. The only thing I've got to say is if you're on Apple platform, you're kind of out of luck. There really aren't any good solutions on Apple. I have bugged Apple about this. Hopefully they'll care one day. But if you're on Linux or Windows or embedded, there are lots of good solutions out there. So that was very quick. I'm going to get now a bit into like how it works and what the different platforms are and stuff. But I'm just going to quickly check on the chat. Do we have any questions? No open questions. Do ask questions in the Q&A on Zoom if you have any. But right now we don't have any. So cool. So where would you use it, right? Well, you can actually use this in production, and people do. But I put an asterisk here because it's not where you want to start, right? It is quite, it's very easy technology to get going with, but it's like anything, right? You'll get better at it the more you use it, and you understand where to deploy it, most importantly. So don't start with production failure. CI/CD is a good place, right? Or actually just that in the loop, like I was saying before. So let's think about how you do this, right? So that's like magical. Is there a non-commercial version of this? Absolutely, there is. If you're on Linux, there is a thing called RR, stands for record replay, and it's really good. It's a little bit limited in like what kind of programs it can work on and where it can work. But if you're writing, for most kind of open source, non-commercial applications, it works really well. So yeah, most people actually start these days with RR if they're on Linux. If you're on Microsoft, if you're on Windows, then there's WinDebug has time travel like baked into it now. It's not in the Visual Studio IDE for some reason, but it is in WinDebug, and again, free to use. How much is the individual license? So I'll get onto that at the end when we get it, because I don't want to make this too much of an advert. So yeah, what happened? So that's what we're talking about, right? When we're debugging, the question is what happened? Well, maybe slightly more precise kind of computer sciencey way of saying is what was the previous state? So how do we go back in time? Well, if I've got really two ways that I might try and do this. I could save all the state as it goes, and this is what the old style GDB process record and some of the kind of early toy type things did. And they would just like save all the state changes. And even if all I'm doing is just saving the deltas, it's still like super expensive to do that, right? Because my computer's doing billions of things every second. Some things changing every single instruction, otherwise it's like live logged. So I'm going to have to store, even at the very, very minimum, I'm going to be storing 8 bytes every single instruction. So that's gigabytes and gigabytes every second. And it's probably going to run very slowly as well, just like saving all that. So saving that state doesn't scale. There's just too much to it. If you think about the power, what we have here, right? We can go back to any line of code that executed, and we can see any piece of program state. That's just a huge amount of data if we do it naively. Even if we store just the deltas, it's just too much at any programming scale. So much better is to recompute it. But then we think about how we're going to recompute the prior states. That's not easy to do, because if I've got a statement like this is inherently reversible. Okay, if I know that A contains 42, and I've just executed the statement A equals A plus 1, then previous line was A was 40, right? That's a reversible statement. But what about that? That's not reversible. I don't know. If I've just executed that statement, I've got no way of knowing what did A contain previously, right? Actually, even the one before is not reversible, because if I'm at that line of code, well, it's going to change the flags and things in the CPU register. But also, I don't actually know what the previous line of code was, right? If I've just executed that, if I've stopped at a breakpoint right after that A equals A plus 1, where was the previous line of code? Probably the one just before, but maybe there was a go-to, right? So you can't run computers backward. It just doesn't work. There's some interesting next-gen research on reversible logic and kind of some of the interesting implications of that. But that's like university stuff. No commodity computer hardware today is reversible. We can't go backwards. So what we do instead is create some snapshots, and we do this, and RR does this, and the WinDebug does a kind of version of this. And we create snapshots, copy and write snapshots. And when in the demo, I'm like stepping backwards one line, what's happening under the hood is it's going back to a snapshot and like playing that forward to just before where we were, right? So recomputing by re-executing prior states. Now, that works because computers are deterministic, right? If you run the same program multiple times with the same starting state and the same set of inputs, it will do the same thing. This is why random numbers are difficult to generate. So we can kind of exploit that, but there's a catch in what I just said, right? So computers are deterministic. Well, computers are deterministic except when they aren't. And I said that if you run it the same program, same starting state, fine, with the same set of inputs. And that's the clincher, right? When we re-execute from that snapshot, we've got to replay all of the non-deterministic inputs so they do exactly the same thing. So we do that through the event log. And you can see this, right? So if I go back to the little demo, how are we for time? Here we go, a little bit of time. So let's have a look. So I can go, I can see the snapshots. So here are all the snapshots in my program. So we've got about 30 of them. I can see they're all kind of at different point in time. There'll still be about 30 actually, no matter how long my program's been running for. And we can look at the event log as well. So info events, this is going to be a lot, but yeah, here are all my events, right? So I've got some signals here and lots of thread actions, lots of thread interactions, right? So these are all the non-deterministic things. I can take one of those prior snapshots now, replay it, and get to exactly where I was. And that's kind of how these things work. Now, there are different kinds of non-deterministic event. If you're on Linux or any Unix type operating system, it's actually fairly well defined. There's 5 of them. You can have, the main one is system calls. Every time I do a system call, I'm going to get potentially a different result. Get time of day, every time it's going to give me a different result, right? Read off the network, any system call is going to give me a different result each time I run it, or may do. But basically what we mean is it's not predictable. I can't predict what the system call will do by the state of the program. And otherwise, it probably shouldn't be a system call, right? It should be a library call. So system calls are kind of the main one. Thread switches, we saw a lot of thread switch events there in the event log. So they are, of course, non-deterministic. So we have to replay them exactly in order. Make sure the ordering is all the same. Signals, asynchronous signals are another one. Some instructions are non-deterministic. So read the timestamp counter will give you a different value each time you run it, even with the same program state. So you have to store those. And what's the other? Read from shared memory. If memory is shared with the process or with the system or the device, then every time you read from that shared memory, you might get a different result, an unpredictable result. So, but we just capture all those 5, which for most programs is a tiny proportion of what they're doing. Like most of which is add these 2 numbers, push this thing on the stack, call this function. That's all completely predictable, repeatable, deterministic. And so that's how we get this ability to scale and to run with very large programs with and very reasonable overhead. Now, there is overhead. Program might run at half speed, maybe worse than that, depending on what your program is doing. But that usually is fine. For most cases, that's fine. And in fact, much better than running with a regular debugger where you hit a breakpoint and you kind of stop, right? And then you have some think time, and then all kinds of things can time out. You can run over all that. A little bit of slowdown. Thing takes a little bit longer, but the time saved overall is enormous. So yeah, that's kind of how it works. Most of the, and this is true of our stuff, but it's true for most of those things out there. So most of the things out there, they recorded the process and operating system boundary, right? So when I'm capturing, and then I'm rewinding that process, and I can capture, and this includes everything that's inside the process, right? So the C library and all of the everything is running in that use level is capturing the recording. And it turns out that the process boundary is a place to do this, because that is where you have the best defined kind of operation. It's kind of, it just turns out you can, it's more efficient and more practical to do it that way. The only other place you can do it actually is at the VM level, which is kind of interesting. And there's some interesting research and some interesting companies doing stuff at the VM level. But most of the things that I'm talking about today, all the things I'm talking about today, they work at the process level. So we record all of the process. Everything that happens inside the process, all the threads, all the functions. And we can, record multiple processes at the same time. That's fine. But it kind of is a process granularity thing. I already talked about this in order. So yeah, what are the big decisions is kind of at what boundaries. Most things, there's even something, there's an interesting company called replay.io, and they're doing browser stuff, right? JavaScript. I know this is a C++ conference, but there's a lot of JavaScript out there. And so they're web application time travel debug. And even they do it at the process level, where they actually didn't have a specialized version of the browser, and that whole browser is like recordable and replayable. So even JavaScript stuff where you think it might be better to do that at the VM level. We have a Java product, by the way, also does it at the process level. So process boundary is kind of the right place to do this. I think that's what we're seeing. Big design decisions between binary rewriting instrumentation or not. So that's one of the differences between the undo stuff and RR, is that we have a JIT binary retranslation of the program as it's running to get our hands in and get that information that we need. Do we store all, some, or no memory accesses? The Microsoft WinDebug will capture most of the memory accesses, actually, and you kind of have to because of the Windows architecture. And do you have separate record replay phases? So, or do you just have like a dynamic kind of interactive debugger? So these are kind of the main ones that I'm talking about: undo, RR, WinDebug, replay.io. This one on the end, omniscient debugger. That's a Java thing that was kind of a prototype kind of from 20 years ago or so, and really was quite pioneering in this. That actually did work at the JVM level rather than the process level. And I think that just meant that it was really cool, but it just didn't scale as well. So those kind of the main design decisions of different things. But most of these, so RR and WinDebug, ODB is kind of old now. RR and WinDebug are free. Undo and replay.io, I think replay.io does have a free tier, but they're a commercial company. We don't have a free tier other than the trial. There was a question about how much is the license. It is the list price for a floating license, so you can share that among your team, is $7,900. How about replaying IO? Absolutely. That's another question on there from David. Totally replay. That's a huge thing, a huge part of it, right? So all the IO is captured. The program receives a message on the network. Well, programs receive a message on the network usually through a system call. So we capture the result of that system call. And then when we replay, we're not really doing any interaction with the network. So I might capture a recording from my data center or wherever I am, take that, put it on my laptop, get on the airplane, even if I'm on one of those older planes without any Wi-Fi, and I can still replay it there, even though it's completely kind of isolated, because all of the I/O was captured in the event log. What if the program runs on bare metal without an OS? Yeah, I should have probably put that in the table. So there's a couple of people who have good solutions there. Lauterbach and Greenhill's Time Machine. Now you need to use the trace modules. You do need the trace macro cell in your embedded system, and it's kind of a hardware-based solution, so it's not cheap. I think they start about $50K, but you've got that option there as well. How does it handle optimized out symbols? I mean, absolutely. It's the same experience as if you were to use a regular debugger. So if you're in the sense you do want that debug info there to be able to do the source level debugging, although you don't need it. It's just optional. You can debug this thing at the machine level. And actually, sometimes people do if they don't have source code or don't have debug info available. So make it practicable. I sometimes joke that this makes the difficult easy and the impossible really difficult. So that totally works. Sometimes you get the dreaded value optimized out whenever you're debugging. The nice thing with time travel is if you get value optimized out, one of those type messages, you can just go back a couple of instructions, reverse step or reverse step I a few places, and the variable becomes live, and you can see what it was. So it's actually a little bit easier to work there. Are there any indication about the host computer state in specified like memory usage or CPU usage? So there's a thing about the CPU usage and memory usage. A bit. We can give you coverage information, for example, and we can give you some performance information. It's not really. You shouldn't think of this as like this. There's a perf and tools like that, and there's Intel VTune, a kind of commercial version of it, and they're really good at telling you about CPU usage and the cache line misses. And like this isn't really about that. That's more about profiling. This stuff is really about debugging or code understanding, not so much the performance level. If it's an algorithmic thing, if you find you've got some kind of order n squared kind of nature to your algorithm that you weren't expecting, it could be really useful then to figure out why is that happening. Or maybe why am I expected to take my optimized path and it went down the slow path? Why was that? So that kind of algorithmic level performance work, absolutely. If it's like, cache line misses and, NUMA things and trying to kind of wring every last CPU cycle out of it, I think things like perf and VTune are probably a better bet for that. So that takes us to the end of the slot. So managed to get it all out there. Had to speak pretty quickly, but we got it all done. Thank you for some really good questions and engagement. And I think that's us done.